So I will start the YouTube transmission, the streaming, please. And then we are going to shut down when you even talk. Ah, she's not there. Okay, so we are now in YouTube. So hi everyone in YouTube, I'm here. We are going to start in 10 minutes. So if any of you want to share your screen or check your sound or something like that, is the moment, I think.
Or get our cups of coffee.
Yeah, sure.
I have a great coffee cup.
I will take this time to get my camera ready because it's not working, and I'll try to do that and get back to the meeting if that's okay.
Yeah, sure.
Okay.
Yeah, our internet went out this morning and I didn't know if it was going to come back in time.
Oh my God.
Yeah, well, it went out earlier in the week for several hours. And I had planned to email my talk so that I could always just do it by phone if I have at least me sitting outside.
Yeah. Oh my God.
But it came back.
We are lucky. Hi, Dr. Prashant.
Hello, good morning.
Hello.
So nice to meet you, all of them, all of you, sorry. At least virtually. So Anna Claire, I don't know how to pronounce your name. Maybe you can tell me. Anna Claire Fabre is
Anne-Claire
like.
Fabre, but yeah, I will understand if you
Sorry.
say Anne-Claire Fabre, it's all right, no worries.
I just love your picture with Anna Shashe. You know, the one you send us, that you have a Shashe. Oh, I just love that. That's funny.
It's my favorite lemur. They're really gentle.
Your name's easy to pronounce compared to your brother's.
That's true. My brother is Pierre-Henri Fabre, so yeah, we all call him PH. It's easier. Our parents disagree with our name, so that's why.
So did my parents. But after I was born, my mother was so tired, my father named me.
So maybe we can start with the introduction. So Dr. Zelditch can have more time. We have a short presentation for introduce all of you. So I will share the screen and Hector will talk.
Okay, yeah, let's start.
Wait me a minute. You can see it?
Mm-hmm.
Yeah. Okay. Well, welcome everyone here in Zoom and in YouTube. This is the last day of the meeting of systematics, biogeography, and evolution. And we'll start today with the diversity and phenotypic evolution symposium. As a first reminder, the chat room will be closed during the talks, but you can write your questions in the questions and answers section here in Zoom. And at the end of each talk, we will read the questions for the speakers, okay? And you can also vote for questions, the ones that are more interesting for you, so that we will read them first. And yeah, remember our code of conduct. You must keep your screens and your microphones closed. And remember that we can follow the discussion through Discord also. So if we don't have enough time here, you can go to Discord after that and ask directly each speaker. And well, let me present our first speaker. It's an honor for all of us to have Miriam Zelditch here talking today. She works at the Museum of Paleontology in the University of Michigan, and she has done much research on the evolutionary dynamics of mammalian skeletal morphology. She uses geometric morphometrics and phylogenetic comparative methods. She's going to talk today about the relationship between diversity and disparity. And she will talk, receive and answer questions in English. The talk is 30 minutes or maybe some minutes, and then we can have a discussion. So Miriam, thank you for being here, and all yours. You can start.
So it's working now. Thank you very much for inviting me. It's been great, and I really look forward to the questions if I finish in time. So my question is, are diversity and disparity linked through time or space? So a question that's long been asked by both evolutionary biologists and ecologists is what accounts for exceptional diversity? An equally important question is what accounts for exceptional disparity, or the variety of the species in these lineages. A classic explanation is God has an inordinate fondness for beetles and also for the tropics. And clearly we can see that God has an inordinate fondness for squirrels. But to ask what those go further into the questions is, do they have the same answer? Are lineages diverse for the same reason that they're disparate? And are lineages diverse and disparate for the same reasons that regions are? Now, diversity and disparity could be linked, could be related through time, and the simplest explanation for that is time. Since all else being equal, older lineages should be more diverse and disparate than younger ones, and regions where lineages originate should be more diverse and disparate than later colonized ones. Or they could be mechanistically related in that one process causes the other. For example, speciation could cause ecological and morphological divergence, or ecological and morphological divergence could cause speciation. Or they could simply have a common cause, ecological opportunity in which unoccupied ecological space leads to both divergence and speciation, or topographic discontinuity and environmental heterogeneity could lead to speciation and divergence. But they could be unrelated within lineages, and that non-adaptive radiations lead to high rates of speciation without ecological or morphological divergence, or iterated radiations in which the same phenotypes are produced rapidly in multiple lineages, has high rates of speciation, but there's no accumulated disparity because the same morphologies repeatedly evolve. And they could be unrelated in regions. If there are different causes of species richness and ecological or functional disparity, as in this study, which concluded that species-rich regions host many species that are apparently functionally redundant. So a general explanation for the coupling is that two landscapes coincide. The adaptive landscape, where the height of the peaks is equivalent to fitness, and geographic landscapes, where here peak height is equal to elevation. Our general explanation for uncoupling is the two landscapes do not coincide. So here we have a single adaptive peak, and we have a much more rugged geographic landscape. So adaptive and geographic landscapes work this out further, and I have to get rid of these pictures or else I can't. I can't see my slides. If the same morphology is well adapted across the geographic landscape, that morphology will be retained as lineages diversify. And if each region has its own optimal morphology, geographically disjunct lineages will diverge as they diversify. So for diversity and disparity, in highly productive regions, many morphologically similar species might be able to coexist within local assemblages. And in heterogeneous regions, differently adapted morphologies could specialize on different resources and therefore coexist within local assemblages. So we can see there could be multiple relationships between adaptive and geographic landscapes. So as my squirrel says, all the stuff about diversity and disparity is very interesting, but what does it have to do with me? And these squirrels are a great model system, well, for everything. But for these studies, because they're broadly distributed geographically on all continents except Australia and Antarctica, and attempts at introducing them in Australia have failed. And regions and lineages show the patterns we want to explain, which is variation in species richness and variation in disparity. So squirrels vary along multiple ecological lines. And one dimension of variation is dietary ecology. And obviously we all know that squirrels eat large hard nuts, but this shows that squirrels can eat a whole variety of things. And here's a not so cute picture. Jaw morphology also diverges along multiple lines, and that's what I'll be focusing on today. So we measure squirrel trophic morphology using mandibles and geometric morphometrics, which allows us to analyze the disparity of shape and size. This shows the main dimensions of jaw shape disparity with lineages color-coded on the left and with phylogeny superimposed on the space of the first two principal components. And we can sort of see that this occupies a large region. This lineage, Calocyanurinae, occupies a large region of the first two dimensions. Here we show, if we quantify the variety or the disparity of the lineages across all dimensions, that there's substantial variation in the amount of disparity across these lineages. As metrics for analyzing phenotypic divergence and disparity across regions, use disparity, which is measured as a variance, divergence rates, which are parameters from a model of phenotypic evolution. And for the geographic analyses, we'll also analyze the phenotypic range and the nearest neighbor distances, which are the distances between the most similar morphologies, including the mean of those distances and the minimum. So methods to analyze correlated rates of divergence and diversification. We followed the procedure used by Adams and colleague, which is to divide the lineages into as many clades as possible with n is greater than 4, measure speciation rates, measure divergence rates, and analyze the correlation by phylogenetic generalized least squares. The procedure was revised by Rybowski and Adams to allow speciation rates to change over time, rather than assuming that they're constant. But divergence rates may also change over time. And constant rates of divergence are modeled by Brownian motion, in which disparity then is a linear function of time. But disparity might not accumulate at a constant rate. And here are at least 3 simple models, on which 2 of them show that disparity does not simply accumulate as a function of time. The problem is that the rate parameters of these models are not comparable to each other. They're mathematically incommensurate. So how could we estimate comparable rates of divergence in order to look at correlations with speciation rates? So what we did is for each clade, we estimated the parameters of the best fitting of the simple evolutionary models. Then using those parameters, we simulated evolution over a fixed time scale. So we then said how much disparity is generated over that unit of time. And that time invariant disparity is what we used as our measure of rate. So here we have all the subdivided clades. The speciation rates were extracted from each small clade from the complete rate model fit to the entire tree using the get clade rates function and BAM tools. And divergence rates were obtained from the simulations for each clade. So here shows speciation rates from BAM. We see 3 accelerations on a background of decreasing rates. One acceleration is chipmunks. Another is on the early branch of marmotine ground squirrels. Whoops, that one is here. And that one is for the Meso or South American tree squirrels. And our result is that we have no correlations. Rates of size and shape evolution are unrelated to speciation rates. And disparity of size and shape are unrelated to species richness. But disparity is correlated with clade age. And put the exclamation mark because it's surprising. That's what's expected if clades evolve at the same Brownian rate. Since they all will accumulate the same amount of disparity over time, time is what explains differences in disparity. But our lineages do not fit that model. So the question is the pattern meaningful? It could be a methodological artifact because we simply arbitrarily subdivided a highly asymmetric tree to get as many data points as possible with each clade having at least 4 species. But it could also be meaningful because the old and most disparate clades are paleotropical and the young and least disparate clades are mainly Western North American. So why might it be meaningful is what we could have is very different adaptive landscapes relative to diversification in those regions. We could have rapid diversification per peak shift in North America. And in the paleotropics, slower diversification and more specialization. So here, we look at modeling adaptive evolution. Adaptive peaks were predicted from diets. And this approach yielded multiple models according to how we interpreted the functional consequence of diets and therefore where we ought to find adaptive peak shifts. And for each model that postulated multiple adaptive peaks, we also fit the equivalent model that predicted different Brownian rates for each diet. In addition to these a priori hypotheses, we used heuristic searches to find the best model as recognized by a particular algorithm. And that's especially useful when species diets are unknown. And it's also a good check on whether our a priori hypotheses are even useful. All the resultant models were evaluated for their relative fit using information criteria. And when feasible, also by parametric bootstrapping, since information criteria tend to be biased in favor of overly complex models, even for simple univariate data. And all these analyses use multivariate data. So this is the best model for each tree squirrel lineage. And we color-coded adaptive peaks. The paleotropical Calocyaurinae have 6 widely spaced adaptive peaks. Some are unique to a single species. The paleotropical Pteromione have no peaks, but 2 distinct Brownian rates. And the specialized folivores have a lower rate, although we really undersampled Pteromione. So I'm not certain that that model would also be the best if we had sampled the lineage better. And the Holarctic neotropical Cyurinae have 3 adaptive peaks. The nut seed eaters, bark gougers, which are all neotropical, and a hard endocarp specialist in Borneo. And as I say, we don't know how it got there. So do the nut and seed specialists of Calocyaurinae and Cyurinae occupy the same peak, which would imply that it's been stable for about 31 million years. And here the statistical results are equivocal. Based on information theoretic criterion, the 2-peak model is very weakly favored because we normally wouldn't say one model is favored over another unless the difference in AIC is at least 4. Here it's only 5. By parametric bootstrapping, which tends to be less biased in favor of more complex models, we get preference for the single peak model. And so what we conclude is over 80% of the lineages combined occupies a single stable peak or two very close ones. And the Holarctic neotropical nut seed specialists occupy one. And actually the tropical nut seed specialists occupy that same one. And the tropical other specialists have diverged along multiple different lines. The best model for the ground squirrels or for marmotany is that there are 7 peaks, none of which is unique to a species. We have 1 peak for the small seed-eating chipmunks, 1 for desert seed eaters, 1 for generalists, that fruit, shrubs, seeds, nuts, and 4 for the grassland specialists, which include specialized grazers, selective herbaceous plant specialists, as well as specialists on pliable versus brittle secondary foods. And the divergence of the grassland, the rapid rate, accelerates where I have that arrow. So the divergence occurs after the speciation rates accelerate. So we find for ground squirrels is that we have multiple peaks, and there's our landscape where they live. So the species lineages are ecologically and morphologically uniform. So what we have is that there's a lot of divergence along multiple lines, which occurs with rapid diversification within those divergent lineages. So why do tree and ground squirrels exhibit such different dynamics? That most tree squirrels are functionally versatile specialists. Being able to eat hard foods is not limiting. The same morphology can eat the hardest nuts of the tropical forest, plus fruits and insects and whatever else they eat, including pizza, ice cream cones. There are fewer Holarctic specialists because the Holarctic climate is limiting. So it's the forests that offer less heterogeneous resources for the divergence of specialized ground tree squirrels. Grazing ground squirrels have multiple ecological strategies. They're not functionally versatile. It's because the adaptations to secondary food sources are limiting, which require different trophic morphologies, or different specializations. And the specializations are specific to the grasslands. Adaptive shifts depend both on grassland expansion and on the divergence of grassland plants. So now we'll look at how diversity and disparity are coupled through time. Species richness is highest in Indomalaya, and the richest regions of Africa and North America have half as many species as Borneo. Disparity, however, does not show that pattern across continents. Disparity is as high in North America as on Borneo. Disparity is exceptionally high in species-poor regions, where a forest and a steppe species are within 20 kilometers of each other. Because those two are very different, the average difference over those two is very large. So how does disparity scale with species richness on continents? Here now we put them on their different scales so we can see the patterns of diversity within continents. And our sample of the African species is really sparse. So we won't try to analyze those geographically. We'll focus on the Old World East and the New World. And the metrics we'll use here is disparity, which is the variance, the range of shapes, which is the sum of the range along all the principal components, and the nearest neighbors, the mean distance between the closest shapes and the minimum distance between the closest shapes. So how does disparity scale? What we did is we divided each of these regions into equal area cells. And for this, we used 20-kilometer resolution. We measured species richness and disparity within each cell. And then we took a random subsample of 1,000 cells. And we used spatial simultaneous autoregressive models, or the SARS error model, with AIC model selection to identify the most appropriate distance for identifying the cell neighborhoods and the most appropriate spatial weight schemes to remove the spatial autocorrelation. These analyses were done in the package species raster, which is still in prep. So what we see is that in the old world east, disparity increases with species richness. But in the new world, disparity is constant with increasing species richness. And that's largely because of the large region where we have just 2 highly divergent species. The range, morphological range, however, increases dramatically in the old world east and the new world. So range increases with species richness. It gets so much higher in the old world because there's more species, higher species richness. The richness and the mean nearest neighbor distance show different patterns. In the old world east, the mean nearest neighbor distance increases with increasing species richness. And in the new world, it's constant. But the richness and the minimum nearest neighbor distance in the old world, it decreases with increasing species richness, and it also does in the new world. So the summary of our geographic patterns, as species richness increases, so do the phenotypic range and minimum nearest neighbor distance. So at a regional scale, we see is niche expansion and niche partitioning. As species richness increases, disparity in the mean nearest neighbor distances increase in Endomalaya, but not the new world. So in the Eastern Old World, the disparity in the mean nearest neighbor distance are highest, where we find both specialized and the functionally versatile tree squirrels. In the New World, disparity in the mean nearest neighbor are highest, where meadows and grasslands are within 20 kilometers of woodlands and forests, where there are just 2 or equivalent numbers of ground and tree squirrel species there. So our conclusions are that diversification and divergence are not correlated through time. Whoops. I still can't get these pictures down there. Diversification and divergence are not correlated through time, but diversity and some metrics of disparity are correlated through space. Much of Sayura diversification occurs by non-adaptive radiations. The dynamics of adaptive evolution depend on the dynamics of resource evolution and on whether adaptations to those resources are limiting. And those processes do not drive speciation. Diversity and disparity within regions may be due to resource heterogeneity. So in this case, the same environmental factor may drive both the maintenance of diversity and disparity. So acknowledgements to our collaborators, especially now Pascal Teitel, who's the one who's doing almost all the work on species raster package, to all the curators who let us photograph their specimens, to our undergraduate assistances, to Access to Everything by Jim Patton. And although most of us don't acknowledge them, acknowledge our development core, without whom none of this would be possible. And for support from the Museum of Vertebrate Zoology. Whoops. Stop share. So.
Thank you, Dr. Zelditch.
Okay, thank you. Well, you had still plenty of time.
Okay, I talk fast when I know I have a lot of slides.
Okay, so we can start with some questions we have here in the questions and answers. For example, the first one, thank you for the talk. I am not familiar with the group, but have you tried correlating with other natural history traits, such as group size, type of shelter used, and social structure?
No, we haven't tried correlating with those. Sociality does evolve more than once, and ground squirrels have been a model system for the evolution of social structure. I don't really know to what extent there would be data on relevant parameters of sociality that could account for either diversity or disparity. What were the other possibilities besides social structure? Group size?
Group size, shelter, type of shelter used.
Well, the tree squirrels use trees as shelter. I mean, they use that for nest-free and predator-free foraging space. Ground squirrels some are fossorial to semi-fossorial. So that's really differing among the lineages rather than explaining diversity or disparity sort of across them, since there aren't general patterns that, I mean, we haven't looked at those primarily because if you do just sort of put them on the tree, they're not going to be very explanatory. But there certainly are factors that we haven't considered, and it might be better to look at aspects of morphology, let's say for shelter or for related to locomotory mode, like whether they're arboreal species or have adaptations for digging. And then if we looked at those morphologies, would expect those to have a high correlation with where they spend their time and how they move around.
Okay. Next question we have, how can we account for extinction dynamics when studying morphological evolution on phylogenies, when we don't have a decent fossil record?
I would say that remains controversial. My feeling is you can't. We have one really, really good fossil sayurid jaw. Well, it's not a sayurid. It's often treated as the ancestral squirrel, but it predates the sayurid musculature. That's sort of diagnostic for the clade. So we have a wonderful jaw of Douglas sayurus jeffersoni 36 million years ago. The change between Douglas sayurus and the optimal calosayurinae or sayurinae morphology is twice as much as between those two lineages. So I didn't put a picture in this talk. It is in the paper, which just came out on evolution. I think it came out in an issue a couple of weeks ago. And there we have a picture that compares what would be ancestral to the crown groups to Douglas sayurus morphology, and shows by how much it's changed and in what directions the living species differ from that. I don't think we can talk about what went extinct in the morphologies unless we have the fossil morphologies and know where they fit in the phylogeny. With teeth, you could obviously do more because you can get teeth from extinct species. And Iris Menendez is doing that. And her results look really exciting. But I don't see how we could get enough jaws of the same quality as the jaws we get from living species from the fossil record. I've only seen maybe one was a line drawing reconstruction, and I don't know what the fossil looks like.
Okay, thank you. We have more questions. Hi, could you talk more about the rule n of clades higher of 4 to perform?
I'm sorry, can you say that again?
Could you talk?
You can, sorry, Hector, you can read, you have an icon Q&A down there, so you can read if you want to, but we can read in loud for the people.
Uh-huh. Can you see it? Hi.
Oh, the idea is that the sample size for testing the correlation is the number of clades you've got. So considering how many clades you would need to demonstrate a statistically significant correlation, even if the value is large, you want to maximize the number of the clades that you've got. But if you have fewer than 4, you really can't begin to think 4 species within one of the clades. You couldn't begin to analyze the phenotypic models. So it's better to have more species within the clades. If you have enough species in the group to get, let's say 20 or more. I mean, ideally we want at least 20 clades to look at. Does that answer the question?
Could be.
Yeah. Sorry.
We can ask the next one. I would like to know if these comparisons can be made in lower scales. For instance, comparisons between species in the same genus inhabiting the Amazon and the Atlantic forest.
I guess the question is which comparisons? Certainly you could do the geographic analyses. One of the problems with analyses of phenotypic evolution is, especially if you're using high dimensional data, you need a lot of species in order to evaluate the models. So some of our, with Pteromyini, we had only 22 species. And that's really too few to evaluate any complex model. The error rates would probably be astronomical, model misspecification rates. Even for univariate data, they tend to be high. When you have, some people have said fewer than 100 species, but I mean, if you're working on mammals, you don't tend to get groups with more than 100 species. So the geographic patterns, it would not be a problem to look at any scale that you want to look at. If you have high species richness, at a low scale, it could even be really interesting, because part of what we're seeing in our results is that Marmotini and Sayurini are really different. So every place where we have the 2 of them, one of each, we have very high disparity. But if we were looking at a lower scale, lower phylogenetic scale, it wouldn't be that sort of the biogeographic history of the continent, which is explaining the results so much as possibly what's happened locally. I didn't know if that answered that question.
Okay, we have another one. Thanks for the great talk, Dr. Zelditch. Where does the diet data for squirrels come from? Also, considering their opportunism when feeding, how expert can a species of rodent be? I also work with rodents and often have difficulty getting dietary data for most species, which sometimes gets in the way of my analysis.
There's a real difference between squirrels and other rodents. Squirrels are diurnal, which means they're active at the same time of day biologists are. And they're the most easily observed. For some species, our diet data are fairly sparse, and that's one of the reasons we also use the heuristic models, is there's a suspicion about what they eat. The reason why we used a variety of different diet classification schemes is because there's often many different diets recorded for the species, since they are opportunistic. There's variation seasonally in diets, there's geographic variation in the diet. So for the better studied species, you get very long lists of what their diets are. For the paleotropical ones, you may get one diet mentioned. The Situation is quite different though for most of the ground squirrels. With the tree squirrels, there are a lot of diets listed, but what their jaws are adapted for is the hardest thing that they can eat. Since they do eat nuts and large hard seeds, whether they eat anything else, and those other things they eat don't require specialized adaptations, as long as they are maintaining the adaptation for being able to eat large hard nuts. The other things are, this is why we say it's not limiting, they're functionally versatile. So we classified those as nut seed eaters for the adaptive peak, because the peak is for being able to eat those hard, large nuts and seeds and everything else that they can eat. Right? It doesn't limit what else they can eat. The reason why we have so many peaks then for the specialized grazers is that they are not functionally versatile. They are adapted to the particular resources that they're eating. So the shifts in the differences in those resources will have consequences for trophic morphology. And we didn't try to correlate just with all the diversity of their diets. We were looking at is what dietary resources predict for trophic morphology.
Okay.
The rest of the question about other rodents, I think it really is difficult for other rodents.
Okay, we can go to next question. This is an interesting one. Since you found such differences comparing South and North hemispheres, do you think the climate also impacted on squirrels diversification?
I think then you probably have to ask how different were the Miocene climates? Because a lot of what we're seeing in the diversification, I mean, I tend to think that all life happened in the Miocene, and what we're just seeing is the residue of what happened in the Miocene. But the climates they're in now aren't the climates in which most of the diversification occurred. So what we'd have to do is go through and look at when each split occurred and what the climates were. I don't think that, I mean, there was a rapid increase. One of the rate accelerations was when the tree squirrels colonized Central and then South America. And the most recent papers I've seen have identified, diagnosed many more species within South America. Although I still have to look at whether there really are that many. But I don't think it's moving into a warmer climate that increased diversification there. I think it was moving into an environment in which there were no squirrels, increased diversification rates there. So I think it would be hard to argue based just on the fact that the current climates are so different that diversification occurred the diversification rates are high within any particular climate.
Okay. We have another one. What do you think of using tip values to perform those correlations, specifically tip rates obtained in BAM or similar approaches? It seems a reasonable approach as using clades, or it may fall into drawbacks you mentioned for low intraclade sampling.
Well, I think the reason for emphasizing that these are tip diversification rates was the recognition that we couldn't get, or Roboski concluded that you can't get reliable extinction rates. So rather than interpreting these as diversification rates, interprets them as speciation rates. I would say that I think it's the best method there is, but it would certainly be useful to have other additional methods. The problem is that every method I know of for trying to estimate rates for lineages that's not simply tipped is imputing branches. I mean, let's say we know that there are missing branches from either because species weren't included in the phylogeny or because they went extinct. And that puts even more emphasis on the model that's used for how do you interpolate the missing data. So I'd say I think this is the best method we've got, but we could certainly use better ones.
Okay. We have time for more questions, right? We have another one. Do you expect the same pattern if look for sexual selective traits?
Well, I guess the question is which pattern? Do sexual selection, if it drives speciation as well as morphological divergence, might show a stronger correlation between diversification and divergence. I don't see how it would affect the geographic patterns, the scaling of diversity and disparity across space. I don't know, I've never worked, except as a methodological collaborator on one paper, I've never worked on a group that had much sexual dimorphism. So I have to say I'm not accustomed to thinking about what sexual dimorphism and sexual selection can do. And when I read papers about it, I'm always stunned at what people are claiming sexual selection can do. But I have no feel for that literature or for those hypotheses. The squirrels obviously can tell that they're sexually dimorphic, but I can't.
Okay. I don't see any more questions. I don't know if we have more questions.
I saw one. It says for Jose Rangel, diversity and disparity are not related with each other. That's a question.
Let me see if I can see that because I didn't understand it. These questions don't seem to be in order, so.
Yeah.
Well, I say diversity and disparity are not related through time in the sense that divergence and speciation aren't related processes. They're governed by different processes or causes. I think disparity and diversity are related geographically. So, I mean, I think we're seeing different patterns with different explanations, whether we're talking about diversity and disparity through time or through space.
Okay, I think we have to move on, but thank you, Dr. Zelditch. It was wonderful your talk. We are happy to have here that you can join us. Thank you.
Thank you.
So we are going to move to the next presentation.
Yeah, maybe we can wait a couple minutes for this.
Yeah.
Okay.
So it will start in 5 minutes.
Sounds good.
So the next speaker will not be transmitted in YouTube, so I will stop sharing our streaming and we come back after a break.